Hi, my name is Benjamin Laterio, and this is my final project for EGR 214 Numerical Methods for Engineers, taught in the fall 2023 semester at Cape Fear Community College. The instructor for this course is Dr. Hans Chapman, and the subject for my presentation is Euler's method in Python. The related course is Calculus 2. Euler's method is a technique for evaluating differential equations without having to solve for the actual analytical solution. It can be summarized using this formula: y sub I plus 1 equals y sub I plus the function evaluated at t sub I and y sub I times h. Now, note that Euler's method is an approximation, and therefore it will have some error compared to the true analytical solution, and that can be seen in this graph, the gap between the two lines. That is the error. In this textbook example, they're using Euler's method to calculate y prime equals 4e to the 0.8 t power minus 0.5 y, with values of t ranging from 0 to 4 with a step size of 1. There is also an initial condition where when t is equal to 0, y is equal to 2. To calculate y1, they are using the value of y when t is equal to 0 plus the function evaluated at the initial condition times the step size. Here you can see they evaluate the function at the initial condition and they get 3. So plugging those values back into this equation, y1 equals 2, which is the value of y when t equals 0, plus the initial condition, the function evaluated at the initial condition that we got from this equation, times the step size, and that equals 5. And you can see when t equals 1, y equals 5, according to Euler's method. For the second step, calculating y2, it's roughly the same process. Instead of using y0 and the function evaluated at 0 and 2, we're using y1 that we calculated from the previous equation plus the function evaluated at t equals 1. So where the function with 1 and 5 being plugged in for t and y. And with this math, you get 11.40216 is the value of y when t equals 2. For this section, they analytically calculated the equation for this differential equation that gives the true solution. So they went from y prime to y, and from then they can just plug in the respective t values to get the y value. And as you can see, in Euler's method, when t equals 1, y is equal to 5, but in the true solution, when t equals 1, y is actually equal to 6.19463, and so there's actually a percentage of error, and that is calculated here. This is the analytical approach that I did by hand for the previous problem. As you can see, it's the same differential equation, the same initial condition, and the same step size. This, for reference, is the Euler's method formula, and as you can see, for all the values of t equals 0 through t equals 4, the values that I have here with the work match up to the textbook answers. And it's really just a matter of plugging in your previous value into the next equation and increasing the values of t as you go along. This is the method for getting the exact solution for the differential equation. For example 1, you have to determine your integrating factor and integrate the given differential equation, and after a little bit of calculus, plugging in the initial condition, you're left with this function, and you can use this to get the true solution to the differential equation by plugging in the increasing values of t and you end up getting the y value for the respective t value. And as you can see here, I'm using that formula calculated in the previous slide, plugging in increasing values of t, and this is the y values for the true solution to the differential equation. And on this slide, I'm just calculating the error percentage between the Euler's solution and the true solution. And as you can see, there's actually quite a bit of error here. And so that could be something to consider when deciding whether or not to use Euler's method or the analytical approach. But in some situations, you are given a differential equation that it is not possible to solve analytically, so the only option is to use Euler's method. This is the Python approach for Euler's method. The libraries that are used in this code are NumPy, Matplotlib, and SciPy. Firstly, we're going to define our differential equation with variables t and y, as well as our t values, our initial condition, and our step size. Secondly, we define the function for Euler's method here using our function, our step size, and our y sub I. In this case, it's y sub n. Then, to actually solve the initial value problem using Euler's method, we have another function called solve IVP, where it creates an array of our increasing t values from 0 to 4 with a step size of 1, and it also creates an array of y values where the first value in the array is our initial condition and the rest of the values are 0. But they will then be replaced with the values of y being calculated with this function for our increasing values of t from 0 to 4. And then it returns t and y. And this is just calling the function with our previously defined variables. Then we can use the ODIENT function to solve the initial value problem analytically to find the true solution with SciPy, and we just define the differential equation one more time, and then we call ODIENT with the differential equation, our initial condition, and our variable. And this is just creating an array of x values so that our graph is a smooth curve instead of jagged. And this is just the code for plotting the two functions with their values on the graph that we'll see in the next slide. And this is the graph that was spit out by the code. And as you can see, it matches up pretty well with the graph that was given in the textbook. You can clearly see the error between the Euler solution and the true solution, and values at the y values at each value of t match up nicely as well. So that is the end of my presentation. Thanks for watching.